Let's go over a couple of examples for this week's discussion quiz. In question 1, we'd like to find the most general antiderivative of f of x, which is 5 minus cosine x minus sine of x plus e to the x. We're going to call it capital F of x, and I'm just going to go through term by term and construct it from each piece. Starting with this 5, I have to think of something whose derivative equals 5, and the most obvious choice would be 5x. Certainly if you take the derivative of this, the x goes away and only 5 is left over. For sine and cosine, it gets tricky when you have positive or negatives. I know if you have a cosine, it should be a sine in your answer, and if it's sine, then it should be cosine. The only thing you have to be careful about is that the positive and the negative is correct. So here, I'm just going to put a space, and I know it has to come from sine. If the derivative of sine is negative cosine, then I'd want a plus sign here. Otherwise, it should be minus. Well, the derivative of sine is positive cosine. Therefore, I have to have a negative here in order for this answer to be negative. So ignoring this, sine goes to cosine. We need this negative, so this matches up, and that's correct for the next part. If we look at sine of x, same idea. I know it had to come from cosine, but do I want this to be positive or negative? Well, if this is positive, the derivative of cosine actually goes to negative sine. You wouldn't want to put a negative here. If you had a negative here, cosine goes to negative sine. We'd have an extra negative making this positive, and therefore I want a plus. We're at the last piece, which is e to the x, and thankfully, e to the x is its own antiderivative. I put a plus c at the end, and this is the answer that I'm looking for. 5x minus sine plus cosine plus e to the x, and that appears to be d. So for this problem, I want to put capital D as my answer in the box. In question 2, we're going to use L'Hopital's rule to solve two limits, and they're both going to involve exponents that have a variable. The approach for all of these is similar, where you'd like to let L equal this limit, and you want to introduce a natural logarithm to remove the exponent. So let's start there. I'm going to take the natural log of both sides of this equation, and I'm going to write this side first. This is the natural log of the limit is equal to the limit as x goes to infinity of the natural log of 1 plus 7 over x. This is all raised to the power of x. The reason for using the logarithm is because there's a property that says you can bring the x down front, and I'll do that next. Okay, if you want to use L'Hopital's rule, you have to have a fraction, and so the trick here is to divide by 1, and we can move this x into the denominator if we write it as 1 over x. That is, this becomes the limit as x goes to infinity of the natural log of 1 plus 7 over x divided by 1 over x. I know this works because if you divide by a fraction, you multiply by its reciprocal, and that would put the x back in the top. And for this, because I have to take the derivatives of these pieces, I'm going to write this as 7x to the negative 1, and I'm going to write this as x to the negative 1. So we have the natural log of 1 plus 7x to the negative 1 divided by x to the negative 1. The thing to note here is, as x goes to infinity, these pieces go to 0. So this thing here is of the form the natural log of 1 over 0, which is 0 over 0. That is an indeterminate form. So for my next step, I'm going to use L'Hopital's rule. I'm going to differentiate the numerator and the denominator separately and hopefully simplify this expression. Starting with the top, the derivative of the log function is 1 divided by what's ever composed inside the function, but then we have to multiply by the derivative of what's composed inside of it. The derivative of 1 plus 7x to the negative 1 is negative 7x to the negative 2. The 1 goes to 0, the negative comes down front, and we subtract 1 from the exponent. The nice thing is, in the denominator, you get negative x to the negative 2. And we see that some stuff cancels. This negative cancels with that negative, And this x to the negative 2 cancels with this x to the negative 2. In fact, this entire denominator is 1, meaning I don't have to write this divided by 1. I'm just going to write this fraction, the 7's left over, and so I'll put that in the top. So this is the limit as x goes to infinity. Again, I'm just writing this fraction with this 7 left over. And I'll rewrite this again as 7 divided by 1 plus, and I'll put 7 over x. I'm writing it this way because as x goes to infinity, that stays 7, this stays 1, and this goes to 0. So this is 7 divided by 1 plus 0, or simply 7 over 1, or 7. Now I gotta be careful. Technically, that's not the answer. This is the natural log of the answer. So we still have to solve for what the limit is equal to. I'm going to put that work at the very top. The natural log of the limit is 7. You can exponentiate both sides with e to simplify the answer. E to the natural log of L is just L. The other side is e to the power of 7. And in fact, that's the final answer to this problem. The limit is equal to e to the power of 7. In part B, we have another limit where there is a variable in the exponent, and we're going to use L'Hopital's rule to solve it. The trick is to, again, call this L. We're going to take the natural log of both sides. And we're doing this so we can remove the variable from the exponent. So once it's expressed like this, we can take this 1 over x and write it here. So this is the limit as x goes to infinity of 1 over x times the natural log of e to the x plus 5x. And this actually is nice because it sets it up as a fraction for us. We can place this thing here. I'm going to write this as the limit as x goes to infinity of the natural log of e to the x plus 5x all over x. Now, is this an indeterminate form as x goes to infinity? And the answer is, yeah, this is of the form infinity over infinity. As x goes to infinity, clearly this goes to infinity. The thing inside the log function goes to infinity, and so is the natural log. So certainly this is infinity over infinity. For this reason, for this next step, we're going to be using L'Hopital's rule. I'll take the derivative of the top and the bottom separately. The denominator is simple. The derivative of x is just 1. The derivative of the top is, for the log function, you get 1 over e to the x plus 5x. But you have to multiply by the derivative of the inside, which is e to the x plus 5. And if you simplify this, this is the limit as x goes to infinity of, so this is e to the x plus 5 divided by e to the x plus 5x. Now, to solve this limit, we're going to use L'Hopital's rule again. This is another infinity over infinity situation. This means, by L'Hopital's rule, this is the limit as x goes to infinity of, the derivative of the top is just e to the x, and the bottom we get e to the x plus 5. You can actually do L'Hopital's rule again. We have another infinity over infinity. And if you do that, we get the limit as x goes to infinity of just e to the x over e to the x, which is the limit as x goes to infinity of the number 1, and therefore the answer is just 1. Now that's for the natural log of the limit. What does the actual limit equal? I'll do that work up here. The natural log of the limit is equal to 1. If you exponentiate both sides, we get from this that the limit is equal to e to the first, or just e, and this is the final answer for this problem.